In this problem, we're looking at the dissociation of water into hydrogen and OH. And we have the Gibbs free energies of H2O and OH and H0. And so the first thing we're going to do is determine delta G0 for this reaction. All right, and that's straightforward. All right, I'm going to come over here and I'm going to put GH2O, and that is minus 237.2. I'm going to go ahead and convert this to joules, so times 1,000, which means I need an equal sign. There we go. And G of OH is minus 157.3 again times 1,000. Okay, and then GH is, well, GH is just 0, the other 0. And if we want the change in Gibbs free energy, what we're going to do is we're going to take the sum of the products minus the sum of the reactants, and we get the change in free energy for this system is 79,900. All right, next we have to calculate KEQ. And for that, we're going to be using delta G is, just a sec, not delta G, minus RT log K. Q. All right, and we just solve this for KEQ, right? So K equivalent is, at equilibrium, is E to the minus delta G over RT. So let's go calculate what that is. What do we need here? We need R. So R is 8.31445. We know T, we need T. So T here is 25, but we need T in Kelvin. So that plus 273.15, being picky with the 0.15. And so now we can talk about this equilibrium, right? And so EXP of minus dG divided by R, and then divided by the temperature in Kelvin. All right, so now we are here. So we know step B, what we're going to have, minus 1.0486 times 10 to the minus 14. Okay. Now we need an expression that relates this K, equilibrium constant, to our concentrations. Well, one of the things you have to pay attention here to is that while the reference concentration for everything else, for all of our solutes, is 1 mole per liter, you can't do the same thing for the solution H2O, right? So the molar concentration of H2O is about 55.5 moles per liter, but that doesn't change much, all right? That doesn't change much. And if you look on page 71 at the equation from which this comes, you'll see in here, these are your solvents, and this is your solute. Ca for water is going to be almost the same. All right, if this is 55, C naught for water is 55.5 moles per liter. this little bitty tiny bit of dissociation is not going to change that much. And so this term isn't there at all. That term isn't there at all. The net is when you get down to the end, you end up with just this K equivalent, or K equilibrium, is the concentration of H plus times the concentration of OH minus. All right, straightforward. Just these terms don't make it through because we're talking about water here instead of some other reactant. Okay, so given that, all right, K, well, we got that. Now OH and H plus, they're in the same concentration, right? You have 1 for 1 on that. And so if you want to calculate them, you can really just go ahead and say this is H plus squared. Right? And so the concentration is going to be H plus, oh, plus. It's just the square root. Okay. Well, in this case, right, H plus square root. Okay. So now you can see, you know, this amount of water dissociating per mole is not going to change the 55 moles per liter concentration of the rest of the water by hardly anything at all. It's not going to be noticeable. So again, we're justified in saying these terms simply don't make it through to our calculations down here because they're going to just, that's going to be log of 1, which is 0. All right, now we know this, and we're after the final step. What is the pH? All right, so what is our pH? Well, we're going to take minus the log of the concentration. All right, and so for this temperature, we're getting the pH is 6.9989. So the pH is ever so slightly acidic at this temperature. pH of water, ever so slightly acidic at this temperature. Hopefully this helps you out in getting through this problem and is another example of using Excel. And I will talk to you later.